So simplicial homology, which we consider now, actually predates the fundamental group and is more elementary than the fundamental group. So let's take a more elementary point of view starting from scratch. Okay, so you could answer the question of how many loops by saying the fundamental group is a free group on 3 generators. Number of generators is determined by the fundamental group. For example, free group by, for example, abelianizing. And so that would happen, but let's try to do this in a more elementary way. What you want to say is that there are 3 loops, okay, or 3 holes. One of them is this guy. Well, there are lots and lots of loops, infinitely many, but independent loops, or which form a basis, there are 3 of them. One is this, one is the red one here, which perhaps I'll draw in this direction. Yeah, so the red one goes up here, and the third was the yellow one, which is not possible to draw because I can't see yellow, so let's make it orange. Okay, so here are 3 loops, and so let's correct this and say independent and I'm going to say cycles rather than loops or holes. This is closely related to loops but slightly different. Okay, and of course the point is that if I'm looking at the gray chap outside, which is this guy, this is also a loop, but I want to think of it as a sum of the red one and the purple one. And what I want to say is that these two guys cancel each other, these two, and leaving the red one and the purple one together, forming the blue loop. And if I happen to choose the purple the other direction, I want to take the negative and reverse it. Similarly, I want to be able to add loops without the nuisance of base points. And the way you get rid of base points is ignore order. So that's what we'll do when we look at loops. Okay, so first thing we'll do is let's put orientations on the edges. Okay, we'll just put some arrows here. Where we put the arrow doesn't matter, but we have to put them for convention. So sometimes it goes this way, sometimes in a loop it doesn't matter. But the thing is, we consider, or rather, okay, so what we have, first thing we have to do is we have to describe loops. Yeah, so what do we mean by this? So we consider edges, by which I mean the edges crossed, with multiplicity. Okay, so here our loops were all simple, they did not cross twice, but you could go around twice, and sign. So we count, for example, here it's going to be, if we have oriented it accordingly, and I call these edges E1, E2 and E3, E3 going up, this purple loop is going to be E1 plus E2 minus E3, but crucially ignoring order. So I wrote it in an arbitrary order. Okay, that's very well. So what we have here is a linear combination of edges. So this can formally be written as an element in C1 is free abelian group. On edges. By the way, here edges are not the pairs that we had. This is a classical graph. If you wish, there are no loops, there are no multiple edges, and we think of each geometric edge as a single edge rather than pairs of edges. So this is a free abelian group on edges. Okay, so we can call it something like Z of E. And our loop is an element of that. But of course, typical element of that is not a loop. You could just have a single edge sitting there like this one. I mean, or finally, if I use yellow here, for example, it could be this lonely edge here. And this is certainly not a loop. Well, we need one property of loops. Okay, so loops. So the property of loops that we have is that every time we enter a vertex, we exit it. But another way of looking at it is, if a vertex is on the boundary of one edge, it should be a boundary of another edge, but with the opposite sign. Okay. So to formalize this, we let C0 is the free abelian group on vertices. This means that we are going to be having a negative. So we are counting how many times we cross a vertex, but with sign. So you could be entering a vertex or exiting a vertex, and that is given by a boundary map from C1 to C0. So the boundary map from C1 to 0, this is called del 1 because it's going from C1, and del 1 of E is going to be the terminal vertex of E minus initial vertex of E. Okay, all this I'm doing geometrically. Formally we will look at simplicial complexes where we have this setting. Okay, and now what are your cycles? Definition: cycles are, more precisely, one cycles are Z1 is going to be kernel of delta 1. Okay, so now this is what, once you are given this, you can actually see there are exactly 3 independent cycles, or more precisely, this in this case is isomorphic to Z cubed. Okay, we did not have to deal with base points and so on, and this also generalizes fairly easily to high dimensions, where instead of just having edges, we also have triangles and such things. The only other thing we comment now before we can set things up to define properly, suppose I filled up one of these sides. Okay, so if I fill this up with blue, then what I would like to say is that this guy has now become 0. So for that we'll also have C2, and we'll also have a boundary map from C2 to C1, and we will quotient and get H1 is going to be Z1 by image of delta 2. Okay, this is what we'll make precise, but first we'll make precise the kind of objects on which this is defined. There are 2 things we can do. We'll start with the very classical simplicial complexes, which are a nice combinatorial object, which are very powerful in many ways, but they're not really efficient at representing a space. So we'll briefly look, when we look at examples, at what Hatcher calls delta complexes, which are more efficient.